Hi, this is Mrs. Doris, and this is Lesson 7-6 entitled Exponential Functions. Our objective in this lesson is that you will evaluate and graph exponential functions. So we're going to begin with the definition of an exponential function. An exponential function is a function of the form y equals a times b to the power of x, where a is not equal to 0, b is greater than 0, and b is not equal to 1, and x is a real number. If you turn in your book to page 453, there are a couple of examples of graphs that show what an exponential function looks like. All right, suppose all the x values in a table have a common difference. If all the y values have a common difference, then the table represents a linear function. If all of the y values have a common ratio, then the table represents an exponential function. And you'll see, that should be TI, sorry. You'll see what we mean in problem 1. Identifying linear and exponential functions. Do the following represent a linear or an exponential function, and explain. All right. Well, first of all, let's look at our x values, and you'll notice in both examples they are going up by 1 each time. The same in this table. Now, they don't have to go up by 1, but we do need to recognize how much x is increasing each time. Now let's look at the y values. In our first table, to get from -1 to +1, you would add 2. 1 plus 2 gives 3. 3 plus 2 gives 5. All right, so what we have is a common difference. And when we have a common difference, we have a linear function. So linear because we have a common difference. In our y values. All right. Another way to look at it is our slope, or our ratio, is the change in y over the change in x, and so we have 2 over 1, which is equal to 2, and that is our common rate of change. Okay, or our slope. In our next example, you'll notice that to get from 3 to 9, we would be adding 6. To get from 9 to 27, we're adding 18. And to get from 27 to 81, we are adding, let's see, 54. All right, so what we want to check here, we know that it is not linear because we don't have a common rate of change. It's going up by different amounts each time, while x is going up by 1. So what we want to check is we want to check on to see if we have a common ratio. Now, to do that, what we're going to do is we're going to compare one y value with the other one. In other words, 9 divided by 3 is equal to 3. All right, we're going to continue to check by taking the next example. 27 divided by 9 is equal to 3 as well. All right, and just to verify, we're going to take our next ratio, which is 81 divided by 27, and that is equal to 3. So because we have a common ratio, we have an exponential function. So exponential function, because we have a common ratio between y values of 3. Problem 2. An initial population of rabbits, of 20 rabbits, triples every half year. The function f of x equals 20 times 3 to the power of x gives the population after x half-year periods. How many rabbits will there be after 3 years? All right, well, all we have to do here, they have already given us the function. Notice that we're starting with 20 rabbits. That's our initial multiplier. It's tripling every half year, so we have a growth factor of 3, and x represents the number of half-year periods. So we're going to take 20 times 3, and since we want 3 years, we're going to take that to the third power. So we end up with 20. 3 to the third power is 27. And when we multiply this out, we find that after 3 years, we're going to have 540 rabbits. All right, and rabbits are typically used in problems like this because they are known for how fast they multiply. All right, problem 3, graphing an exponential function. All right, this again is something where you will want to use your calculator to do, and it's just a matter of substituting in your value of x into the function itself. So, for instance, in our first example, we're going to take 0.5 times 3 to the negative 2. In our next example, we'll take 5/10 times 3 to the negative 1. In our next example, we'll take 5/10 times 3 to the 0. And that one is easy for us to go ahead and evaluate. We know that 3 to the 0 power is 1, and 5/10 times 1 would be 5/10. So we have the ordered pair. I may not have room to write here. X is 0, y is 5/10. Let's do the next one. 5/10 times 3 to the first power. I think we can do this mentally as well. 3 to the first power is 3, and 5/10 times 3 is 1.5. So we have the ordered pair 1, 1.5. And I bet we can do the next one as well. We have 0.5 times 3 to the second power. 3 to the second power is 9, and 9 times 5/10 would be 4.5. So we have the ordered pair 2 and 4.5. All right, so let's get our calculators and evaluate the others. We have 0.5 times 3 raised to the negative 2 power. And we're going to round this off. We get 0.0, we'll just round it up to 0.6. What you get is 0.0 and then a whole string of 5s. All right, so this is an approximate value. So negative 2, 0.06. All right, let's take the next one, 0.5 times 3 raised to the negative 1 power. And we get 0, 0.1, and a string of 6s. So we'll round that up to 7. And so our ordered pair is negative 1 and 1700ths. All right, so let us graph this exponential function. Negative 2 and 0.06, well, that's just right almost on the line because it is so tiny. Likewise, at negative 1, a little bit more, but not much. At 0, it is 1/2, 0.5 or 5/10. At 1, it's 1.5. And at 2, it is 4 and 5/10. And so this is what is called an exponential function. When it curves like this, and it's either going to be going rapidly up, this would be a growth model, which we'll talk more about in the next lesson. If it was going down, it would be an exponential decay type of function. All right, let's do another one. This time it's very similar, and so we won't have to do too much more work, but our beginning number is now negative 5/10. All right, so once again, we're going to take negative 5/10 times 3 to the negative 2, negative 5/10 times 3 to the negative 1, negative 5/10 times 3 to the 0, which of course is just going to be negative 5/10, and negative 5/10 times 3 to the first, which will be negative 1 and 5/10, and negative 5/10 times 3 squared, which is going to be negative 4.5. All right, and because this is just similar, except for the fact that we are getting a negative answer, I think we can go back to our previous graph and get our numbers. Our y values simply are going to be negative. So going to be for negative 2, x equals negative 2, we'll have a negative 600ths, and for negative 1, we'll have a negative 1700ths. All right, so graphing this model. At negative 2, we've got a point just right, almost on the line. Likewise, at negative 1, 1700ths is even closer to the line than I'm able to show it. At 0, negative 1/2. At 1, it's negative 1.5. And at 2, it's negative, let's see, 1, 2, 3, right here. So once again, this is a good example of a decreasing model. It will continue, y will continue to get smaller and smaller. All right, in our last problem for this lesson, we're going to graph an exponential model. A new museum had 7,500 visitors this year. The museum curators expect the number of visitors to grow by 5% each year. The function y equals 7,500 times 1 and 500ths raised to the x power models the predicted number of visitors each year after x years, and graph the function. All right, and once again, we're going to learn more about this in the next lesson. This is an exponential growth model, and we kind of have a clue to that in the wording. They're expecting the number of visitors to grow by 5%. And the 5% is reflected in our factor right here by the 0.05. The 1 represents 100%. So that means that they expect the same number of visitors next year plus 5% more. All right, so let's graph our function. And we're going to take several values and we'll set up our table very similarly to the way that we did on the previous problem. So we'll take 7,500 times 1.05 and we will raise that to the x power, whatever we choose for our x. And then that will give us our y. And I may need a bigger column than that. And I don't see the need, I don't think that we really need to write the x, y because we have a column for each one of those. So I'm going to leave that column off. All right, well, let's start right now. And that's pretty easy. We'll start at year 0. All right, so we have 7,500 times 1.05 raised to the 0 power. And we can do this one in our heads. Anything to the 0 power is 1. So 7,500 times 1 is 7,500. All right, so that's this year. Okay, let's go on to next year. After 1 year, we're going to take 7,500 times 1.05 raised to the first power. And again, please practice putting these into your calculator, making sure you get the same answers that I do. If you have a question or don't get that answer, then please ask and I will be glad to show you. All right, so with a 5% increase after 1 year, they should expect 7,875 visitors. Let's go after 2 years. All right, so 7,500 times 1.05, and we're going to now raise that to the power of 2. All right, so type this into your calculator. And we get a fractional answer. And of course, we can't have, it's 0.75, we can't have 3/4 of a visitor, but we will go ahead and round to the nearest visitor. So it would be 8,269 visitors. All right, let's do just a couple more. Let's go 3 years. 7,500 times 0.05 raised to the 3rd power. And we get 8,682, again needing to round it. All right. And why don't we skip year 4? Let's go to year 5 and see what happens. So 7,500 times 1.05 to the 5th power. And we get 9,572. All right, so let's graph this information in our table. X represents the year. We'll just call it number of years. Okay. All right, so let's see. I believe, I think I can skip every other one. There's 1, 2, 3, 4, 5. All right. On our vertical axis or our y-axis, we're going to have the number of visitors. All right, and I didn't give myself very much room here to write. You should have room in your margin to write. We're going to start at 7,500, so we may very well use a break in our graph here. And so I'm going to start at 7,000. And because of my lack of room, I'm just going to show 7. So in my title, number of visitors, I'm going to put in thousands. All right, sorry about that. Okay, so let's see. Let's go, this will be 7,200. How about 7,500? 8 we'll put right there. 1, 2, 3, 4. 1, 2, 3. There would be 9. 1, 2, 3, and here's 10,000. All right, so let's graph our numbers as best we can. Year 0, 7,500 would be right here. Let me use a different color so that kind of stands out. In year 1, 7,875. All right, so this would be 7,750, and so it's going to be slightly higher than that. In year 2, 8,269, and let's see, so it's going to be slightly above the 8,250 mark. In 3 years, 8,000. 682, which is going to be up in this area. And after 5 years, 9,572. So right about here. And all right, now this may look kind of like a straight line, and that's because the growth is very small each year, 5% each year. But the more years you carry it out, then you are much more likely to see a curve to the line. And so it's kind of hard to see here, and I'm not sure I've got some of my points exactly in the proper space. So be careful with your graphing, and we'll do some more problems similar to this in your exercises. If you have any questions, please do not hesitate to ask.